So for this one, actually, the potential at any point on the central axis with this axis, the z-axis of a uniform charge disk. We have derived the E view of this disk on z direction during chapter 22, I think. Yeah, and maybe also for chapter 23. No, chapter 22. Chapter 22. You can check the slides. We have used the integral, to integrate many ring, which will generate the E view at this point, and then we just add them together by an integral. And now for the previous page, like here, so we have derived the electric potential at this point. So we can use this simple formula to calculate the electric field like this. Actually, for the on this axis, you can see that the E view on x and y direction will be 0 because due to the symmetry, so there shouldn't be any E x or E y should be 0. The only possible direction should be in z direction. So Ez would be something like minus v z, something like this. Because actually for this one it is in 3 dimensions, but you can separate in every dimension like this. Ex will be minus dv dx, ey will be minus dv dy, and so on. So for this one, or you can either write round or d. It doesn't really matter in this case. So we have this one in the 2 previous page, so that we can take the derivative. So the first term is the constant, so nothing special. And the second term, this one, z squared plus r squared and square root. So it will be something like z squared plus r squared, and then z. Okay, and the next term minus z is very simple, minus 1. So if you want to write it like this is a negative sign here. There's a negative sign here. Negative sign. So it will be something like this. 1 minus. Actually, we just distribute this minus sign into the bracket. And actually, this is what we derive in chapter 22 using the integral. So that's why we need to define the electric potential, because calculating V is simpler because it is a scalar. So we don't need to do many vector decomposition, and then we add the small vectors according to different axes, and then there are more steps to do, but here for adding a scalar, so it will be simpler, and then we can use the gradient to find the E field. 不是，这个是在这一页我们是 in these slides we can derive 3 like this using these steps, and actually we can use this equation to find E. So we don't really need to do the integration, just what we did in chapter 22. We need to calculate the E generated by every small ring, and then we integrate them together. This is supposed to be a simpler method. Any other questions? So actually, this is what we derive. So here we define, actually we have already defined the electric potential energy, and actually here we need to calculate the electric potential energy due to charged particles. Actually, the electric potential energy of a system charged particles is equal to the work needed to assemble the system, with the particle initially at rest and infinite distance from each other. So, which means if there are only one charged particle, there are no electric potential energy stored in this system. Whenever I put the second one in this system, you need to spend this energy to put the second charged particle here. So after this, if I want to put the third one to maybe like here, then you need to calculate the energy between Q1 and Q3 and Q2 and Q3. Maybe I just put a particle somewhere like here. If I just put, no matter it can be positive or negative, maybe positive Q3, then there will be potential energy between Q1 and Q3 and Q2 and Q3. If I put the fourth one, maybe negative, then there will be potential energy between Q1 and Q4, Q2 and Q4, Q3 and Q4. So for this one, if the total energy of a system particle is sum of the potential energy for every pair of particle in the system. So you can see the summation here. It just write I is not equal to 0, which means there will be something like n choose 2 term, or you can write it like this. If there are 5 particles, there will be 5 times C52 will be something like 5 times 4 over 2. I suppose you have learned the probability. So if there are 5 particles, there will be 10 terms. If there are 6 particles, something like 6 times 5 over 2, which is 15, something like that. Which means that for this case, so Q1 and Q2, Q1 and Q3, Q2 and Q1 and Q2, Q1 and Q3, and Q2 and Q3. So three combination of for 3 particles. If there are 4, Q1 and Q2, Q1 and Q3, Q1 and Q4, so 3, and Q2 and Q1 is repeated, so we don't count it. Q2 and Q3, 2 and Q4, 2, 3, 2, and then Q3 and Q4. So 1. So for 4 particles, 4 times 3 over 2, 6 combination, okay? Which means if you put one additional charge particle inside, then there will be electric potential energy between all of them. You need to count from 1 to n-1 particle. So actually, this one is a 2-dimensional summation. It would be something like this. Something like this. Something like this. Here we have like this. And actually, these two are the same, so we only count the upper triangle or the lower triangle, either one of them. So for this one, you have three terms, 1, 2, 1, 3, and 2, 3, something like that. Okay, I think it should be clear enough. So for this one, there are three-point charge held in a fixed position by forces that are not shown, which is the electric potential energy U of the system of charge. Assume D, Q1, Q2, and Q3, in which Q equals this. So actually, we just need to calculate total U. U will be U12 plus U23 plus U31. So it will be something like 1/4 pi epsilon 0 Q1 Q2 over D plus Q2 Q3 over D Q3 Q1 over D. Yeah, because it's with equal sign or D. So this one is quite simple, and actually it will be something like 0.12 1 minus 4 plus minus 4 2 plus 2 times 1 times 150 times 10 to minus 9. So the answer will be minus 1.7 times 10 to minus 2 joule. So you need to be careful about the sign. Actually, if positive sign, you plug in positive value. If it's negative charge, you plug in negative value. So if one is positive, one is negative, then the potential energy will be negative because they tend to attract each other. If you really need to hold it, actually it gives you some potential rather than you need to give some work done to do that. If they are same size, then like this, 3 and 1 are both positive, so that you need some work done. And actually, for this system, this is positive, this is negative. They tend to attract each other. Actually, only at this moment they can be whole like this. So for the next sample, okay, you can see an alpha particle, 2 proton and 2 neutron. This is alpha particle. Move into a stationary gold atom. Gold atom is very large, 79 proton and 118 neutrons, passing through the electron region that surround the gold nuclear shell and head toward the nuclear. So actually, the alpha particle coming from there and try to collide with the gold nuclear, and actually it cannot really touch the nuclear. It will go back somewhere because it does not have enough kinetic energy to really move close to the gold nuclear because they have some charge. This is two protons. This one 79 protons. So they will repel each other. But as long as it has some kinetic energy to move close to the gold nucleus, then it can move somewhere and then it will go back. The alpha particle slow until it momentarily stop. So it will stop here, and then there are some actually during this period there are some repelling force, but when it moves closer, the force will be even larger. So you try to slow down it and then until it stop and go back. So you momentarily stop when its center is at the radial distance r equals 9.23 femtometer. Femtometer is 10 to minus 15 meter. Then you move that along its incoming path because the gold. What was the kinetic energy Ki when it was initially far away? Hence the external to the gold atom. Assume that the only force acting on between the alpha particle and gold nuclear is the Coulomb force. So actually we have something like the conservative of the sorry. What? So we have something like the conservative of the mechanical energy, the initial kinetic energy and the initial potential, and the final kinetic energy and the final potential. So actually, you need to find Ki. You actually need to find Ki. And we assume this to be 0. Also, this one would be 0 also because it momentarily stops here. So no velocity. So no kinetic energy. So Ki will be UF, which is K is two proton, one is 2 proton, one is 79 proton, and the distance is 9.23 times 10 to minus 15. And actually, we still need to multiply 1.6 times 10 to minus 19 squared, which is the charge of a proton or an electron. So, what? 3.94 times 10 to minus 12 joule. Huh? Because it is mentioned that initially we'll assume the alpha particle is far away here. It's far away from the nucleus, so the potential energy will be zero. Something like you can assume R to be infinity, so U will be zero. Oh, but it will be, you will assume it is much smaller than that one. Because it didn't tell you, so you assume far away means infinity. Maybe, but it will be very complicated because all the electrons are moving. Actually, you have no idea where will be the electron. Even you are outside, but you can say much far away from the nucleus. And actually, there are another unit for the optics guy. They can divide this energy by 1.6 times 10 to minus 19, which will be equal to this EV. This M is mega, 10 to 6. And actually, EV will be the electron volt, which is something like the energy for a electron. Okay, so this one tells you that, okay, this is more informative stuff. Potential of a charge isolated conductor. So for this graph, it tells you that an excessive charge placed on an isolated conductor will distribute itself on the surface, only on the surface, so that all points of the conductor, whether on the surface or inside, come to the same potential. This is true even if the conductor had an internal cavity, and even if that cavity contains a net charge, which means that it tells you that if lightning hits the car and this guy is inside the car, then he will be safe. It's wise to enclose yourself in a cavity inside the conductor cell where the electric field is guaranteed to be zero. A car, unless it is convertible or made with a plastic body, it is almost ideal. Believe it or not, we mentioned that if you are in a car, you will be safe. to be hit by lightning. And actually, from a physics point of view, the voltage potential is something like this. Actually, imagine that inside the car there is some voltage, but actually for every point inside the car, the voltage go up to be an equal value, so that as you have learned the circuit analysis, if there are no voltage potential, then no current, so no power. So the guy won't be damaged by the lightning. And actually, you can use this formula to calculate the electric potential. So there will be no electric field inside. So actually, from chapter 21 to chapter 24, we have defined many variables, something like the electrostatic force, the electric field, electric potential, and the electric potential energy. I suppose you'll be very confused. When I grade quiz 1, I already feel that some of you cannot distinguish between F and E and something like that. And for this chapter, it comes the V and also U. So it might be very confused. Actually, I try to write an analogy about the sword art online, but I think it's not really perfect. So I just remove that 2 or 3 sides. And so it comes up with a summary like this. Okay, so in chapter 21, we define the electrostatic force F like this, and for chapter 22, the electric field is something like this. For chapter 24, this chapter, potential energy, electric potential energy, and the electric potential. So actually, for that two, F and E are vectors, and U and V are scalar. So between them, you just multiply Q0, the test charge, so that you can change from E to F or F to E. And similarly, for U and V, you also multiply Q0 or divide Q0 between them. And in this chapter, you have seen 2 formulas. One is like this for the beginning, and this one just now. So actually, you just integrate E, then you have V, and you take derivative of V, you get E. Similar like this. If you learn physics, you also see this formula. Actually, in high school, something like this, we don't have the integral, so we just multiply F dot, maybe multiply by the displacement, then it will be the work done or the potential. So I think these 4 variables are the most important variables for the electrostatics. Actually, chapter 25 and chapter 26 will also be something about the electrostatics. I don't mean they are not important, but from the structure point of view, I think these 4 variables are on top of the physics. For chapter 25 will be capacitor, chapter 26 will be resistor. So actually this is some application for this variable, and they try to derive some lump circuit model which you use in the circuit analysis. I think the logic flow will be something like that. Okay, we'll have some additional example. Maybe okay, maybe we have a break first. Maybe